So I want to walk through an example of approximating area that's going to be very similar to the practice exercises and homework assignment that you're working on in Lesson 6.3. Let me remind you first about our steps and the things that we like to write down when we're doing these problems. So I had this slide in the last video, and this is sort of a list of the things that we want to accomplish in order to find an approximation for the area between the curve and the x-axis. So basically, as you know, we're going to identify our function and the interval that we're looking at. We're going to sketch a graph. Once we know the number of rectangles we're going to use for our approximation, we find the width of each rectangle, delta x. We just do b minus a over n. It's important to make a list of the subintervals and then the representative x values that we're going to use, whether it's the left-hand endpoint, the right-hand endpoint, the midpoint. And then we calculate f of x for each of those x's. We add those up and we multiply by delta x. That's our area approximation, and then make sure that you're answering the question posed. Let's try that on a problem straight from the textbook. So here you have problem 5 from lesson 6.3 in our text, and we're going to be approximating the area under the curve 4 minus 2x. Let me just outline the 4 things that we're going to have to do in this problem, because they're very similar to several of the problems that you're going to have to work on. And then we'll go ahead and find a solution to each part. First thing we're going to do is sketch a graph of the region. Our interval is 0, 2. They also want us to use geometry to find the exact area. This particular shape is going to be a triangle, and we can actually figure out the area. We're also going to use our Riemann Sum, which is the name for the approximation that we're going to calculate with the rectangles. We're going to use 5 rectangles. And the important piece that we need to keep an eye on here is that we want to use the left-hand endpoints. Then in part C, they're going to make us do it all over again, but this time we're going to use 10 subintervals. In other words, 10 rectangles. N equals 10. We're still going to use the left-hand endpoints. And then finally, we're going to compare these two approximations in B and C with the exact value that we found in A. And we want to see if the approximations are getting closer to the exact value as we make n larger. We want to make sure that it's improving as n gets bigger. Okay, so let's attack this thing. I'm going to clear the screen here and start working. So I'm going to get organized to solve part A here. My function is f of x equals 4 minus 2x. That is a linear function, the negative slope. Remember that we're doing, well, let's start by drawing the picture and then finding the exact value. We'll do the subintervals in a second. Okay, so I'm only worried about the x-axis from 0 to 2. And this line comes down like this. I just missed it, but that's pretty close. The region R that we are interested in is this area in here. Now this is a triangle, as I said, and we can easily calculate the exact value. It's just 1/2 times the base, which is 2 units, times the height, which is 4. So the actual area of region R is in fact 4 square units. The reason we're able to do that is this thing does not have a curvy boundary. It's straight. So it makes a geometric shape. We're still going to practice our approximations on this thing though. So the answer to letter A anyway is 4 square units. Okay. In part B, we are asked to find an approximation with 5 subintervals. So our n is 5. Basically, I'm going to draw 5 rectangles. Or we are going to approximate this as 5 rectangles. I'm actually not going to draw 5 rectangles. This picture is bad enough as it is. But keep in mind, this is going to be a typical rectangle. We are using the left-hand side as the measurement for the height. We're using the left-hand point, which has got to be determined by the blue line. So our approximation is going to be a little high because all of our rectangles are going to be on the high side of that blue line. The width of our rectangles is delta x, which we calculate by doing b minus a, which is 2 minus 0 over 5. So that's 2/5. If you're using decimals, it's 0.4. That means that the subintervals down here on the x-axis are going to be bounded as follows. The first interval will go from 0 to 0.4. The next one will go from 0.4 to 0.8. The next one will go from 0.8 to 1.2. And the last one will go from, oh, it's not the last one. The next one will go from 1.2 to 1.6, and the last one goes from 1.6 to 4. Since we're using the left-hand endpoint of each interval, see, here's my subintervals. If we're using the left-hand endpoint, we're basically only talking about 0, 4, 0.4, 0.8, 1.2, and 1.6. 4 is a right-hand endpoint. It's not a left-hand endpoint. Now we're going to be plugging 0, 0.4, 0.8, 1.2, and 1.6 into our function to get the heights of each rectangle. And then, we're going to multiply by delta x. We just factored it out. So here's the approximation for my area. If you'll permit me, I'm going to write it down here so I have a little bit more room, but this is still part of part B. A is going to be approximately equal to f of 0, which is 4, plus f of 0.4. When you put 0.4 in, 2 times 0.4 is 0.8, and 4 minus 0.8 is 3.2. F of 0.8 multiplied by 2, 0.8 times 0.2 is 1.6. 4 minus 1.6 is 2.4. F of 1.2, you double that, you get 2.4. And 4 minus 2.4 is 1.6. And then finally, when we put in 1.6, we double that, we get 3.2. 4 minus 3.2 is 0.8. Those are all the heights, and then we're going to multiply that by the width, which was 0.4. My calculations give me 12 for the sum in the parentheses times 0.4, and so this works out to be an estimate of 4.8 square units. I'm getting 4.8 square units for my estimate. Now, as we said, that's a little high. We know the exact value is 4. But this particular strategy where we're using the left-hand endpoint means that every single rectangle will be above. And remember, I have 5 of them, even though I've only drawn 1. Every single rectangle is above, and when you add them up, you get 4.8. Let's see if increasing the number of rectangles will improve that estimate. So in part C, we're going to do the same problem again, but this time n equals 10. F of x is still 4 minus 2x. This time delta x is going to be 2 minus 0 over 10, which is 1/5 or 0.2. So we're going to have 10 subintervals, and they're going to look like this. The first one will go from 0 to 0.2. The next one goes from 0.2 to 0.4. The next one goes from 0.4 to 0.6. The next one goes from 0.6 to 0.8. Next one goes from 0.8 to 1. Then 1 to 1.2. 1.2 to 1.4. 1.4 to 1.6. 1.6, oops, I get ahead of myself there. 1.6 to 1.8. And finally 1.8 to 2. let me just show you that this is, in fact, 10 subintervals. Remember, these are all x values, so we're going from 0 to 0.2. That's 1, there's 2, there's 3, there's 4, there's 5, there's 6, 7, 8. Huh. See what I did there? Just pretend that number's not there. Blooper reel. 9 and 10. Okay. Why don't I sketch this picture just to remind you what it looks like. It's the same one as before. In general, we had that line coming down like this, and basically we're going to draw 10 rectangles. We're getting the left-hand endpoint on each one. I hope I fit them all in there. Yeah, pretty good. Okay, so we have these 10 rectangles. Each of them has a width of 0.2. We're going to figure out the heights, just like we did before, by plugging the left-hand value of our endpoints into the function f of x. So what we're talking about is we're going to plug each of these numbers except 2, because we're taking the left-hand endpoint of each interval, into the function, and we'll approximate the area that way. So this is going to be a long expression, but basically our area is approximately, excuse me, when you plug in 0, we still get 4. When you plug in 0.2 and double it, you get 0.4, and 4 minus 0.4 is 3.6. When you plug in 4 and double it, you get 0.8. 4 minus 0.8 is 3.2. And then what you're going to notice is that each time you go down by 0.4. So I'm going to speed this up a little bit, and I'll list the rest of the values. I might not even talk too much while I'm doing this, because I'm sure after a while you probably get tired of hearing me talk. And I'm going to run out of space here, so we'll just nudge it down here. And all of this, remember, gets multiplied by our delta x, which is 0.2. I apologize for not squeezing that in there. Okay, believe it or not, when you add all this up, we get 22 for the sum, and then we have to multiply that by 0.2, and that turns out to be 4.4 square units. Okay, again, it's still on the high side of 4, which is our exact value. You don't know this, but a bug just crawled onto my back and scared me. I'm going to pause. And I'm back. Took care of the bug. Anyway, as I was saying, we increased the number of rectangles. Our estimate is closer to the exact value of 4. Still a little on the high side, because all of our rectangles, as you know, looking at this picture over here, all of our rectangles are on the high side of our blue line. Okay, so let's wrap this problem up with letter D and talk about whether or not we think that our approximations are improving. So just to summarize, we had an exact value of 4 square units using geometry. When we did n equals 5 subintervals, 5 rectangles, our approximation was 4.8. And when we did n equals 10 rectangles, our approximation was 4.4. These are all in square units. So the answer to the question, is the approximation improving as n gets bigger, is a big, huge yes. Okay, so that's the process that you're going to have to do on your homework when you're approximating area. Basically, we're just adding up rectangles, so try not to get too caught up in this big concept of curvy regions, think curvy regions bounded by curves and things like that. And don't worry about bugs jumping on your neck when you're in the middle of doing the math either. But just keep in mind that we're adding up rectangles and that we're trying to approximate the area of these interesting regions. Good luck.